One thing you're going to need to remember for today is how to write the equation of a line. So I would just start with y equals mx plus b, and then since you need your slope, you can do rise over run. So your rise vertically would be your y values, and then your run horizontally would be your x's. So if you subtract the y values of your 2 points on top, and then keep the same order and subtract your x values on bottom. For this line, it's gonna have 5 and 4 that you subtract, and 2 and, your other x coordinates, -1. You're gonna end up with a slope of 1/3. So you've got your slope, but you still need your y-intercept. So you have an x and y value that you can use to get that y-intercept if you plug them in for x and y. So pick either point. I'm gonna go with 2, 5, because it's positive. Plug those values in for your x and y coordinates, and then do a little bit of simplifying. Multiply would give you 2/3. If you subtract 2/3 from both sides of your equation, you're gonna get, okay, I was gonna do common denominator, but I'm just gonna do mixed number and make that 4 and 1/3 for your y-intercept. So putting it all together, your equation of your line is y equals 1/3 x plus 4 and 1/3. So in your activity, we were looking at scatter plots, and we're gonna measure some relationships between points on scatter plots today. Specifically, we're going to be looking at this thing called correlation, which basically is a measure of how closely your points are gonna fit to a straight line. So you can have points that have a positive correlation. These are linear correlations that we're looking at today. So how close your points lie to a straight line. So if your x values increase and your y values also increase, then that would be data that is a positive correlation. Like say your amount of time that you study, as that increases, we would hope that your grade, your output would also increase. So those data values would have a positive linear correlation. If two variables have a negative correlation, then that means as your x values increase, your y values decrease. So something like, if I am out shopping and the amount of money that I have left in my wallet is what we're measuring, then when I walk into the store, I have some money, and then as I put things in my cart, go from one store to the next, the amount of money that I have left is going to be decreasing, so that would be a negative linear correlation coefficient. So you can look at your scatter plots and kind of think about would those points lie close to a line with a positive slope or close to a line with a negative slope, to think about if it's a positive or negative correlation. So the correlation coefficient is the number that actually measures how closely your points are to lying on a straight line. So it's a number between -1 and +1. They use r for the variable to represent it. So if you have data values that are just kind of all over the place, there's not really a correlation between the two variables, say like age and IQ score. Those two things are unrelated. Your data points, if you were to put those in ordered pairs, would be all over the place. They'd have a correlation of 0 if there's no correlation. If your points are almost perfectly on a straight line that has a positive slope, then your correlation coefficient is 1. If they're perfectly on a line that has a negative slope, then your correlation coefficient is -1. So 1 and -1 are basically like make perfect straight lines. You can have correlation coefficients in between where your data points look like they're fairly close maybe to a straight line, but a straight line wouldn't go through all of them. You can maybe have like a correlation coefficient of -0.5 if they are sort of spread out a little bit, or a correlation coefficient of +0.5 if they are spread out a little bit from a line with a positive slope, and anywhere in between. It's a scale. Points that have a correlation coefficient close to 1 or -1 have a strong positive or negative correlation because they're very closely related to one another. The closer you get to 0, like a correlation coefficient of like 0.2 or -0.3, those are weaker correlations where there's some relationship but not a strong one, and then 0 is like no correlation. So we're going to describe the correlation as either positive or negative. I like to draw a kind of line to see if it would have a positive slope or a negative slope to fit my data. So this line that fits my data would have a positive slope, so it's a positive correlation. As my x values increase, so do my y's. R is kind of an approximation here. I would say that my points are like reasonably close to lying on that line that I drew. So I'm going to have my correlation be closer to 1 than to 0. But they are a little bit spread out from it, so it shouldn't be super close to 1. Anywhere from maybe 0.6 to 0.7, 0.8 would be an acceptable correlation coefficient. So if I look at this next one, it does look like my points are kind of trending downwards as my x values increase, my y values are decreasing. So this is going to be a negative correlation. Now these are much more spread out from my line than my previous points are. So my correlation coefficient should be closer to 0, maybe say negative 0.3, negative 0.2, because they're fairly spread out. Remember, the further that they are from lying on a perfect straight line, the closer your correlation coefficient is to 0. And this one does need to be negative because they're decreasing. So let's look at one more. This looks like I could draw lines all over the place, and none of them would really match the trend of my data. So if you can't see a relationship between your variables, that means you have no correlation, and your correlation coefficient is 0. These are linear correlations, remember, that we're measuring with this correlation coefficient today. So you can have data that has a non-linear relationship. So say that I've got a scatter plot of points that looks like, whoops, random scroll, this. My correlation coefficient, if I tried to calculate it, my linear one would be 0, but that data definitely has a nonlinear correlation because it is very close to lying on a quadratic function. So that actually has a strong correlation. It's just a nonlinear one, not measured by our R value. There are other ways to measure nonlinear correlation. We're going to make some lines of best fit, which you may have done before. But these are linear models, so straight lines, that best match the data. So as close to meeting our data values as we can. So you're going to take your data points, put them on a scatter plot. You might have to try a couple times to draw in a line to match your data. You're going to choose 2 points on the line you drew. So that's key. They have to be on the line that you drew. And then you are going to write an equation of a line that passes through those 2 points. So let's do one. Say that I have these 5 ordered pairs for my data. I want to go ahead and plot them on my axis. So scale is kind of key here. You want to make it so that all of your data values fit, but you don't want to like squish them all together because then it's really tiny and very difficult to get a good estimate for. So I'm going to count by tens on my y's since I'm going from 0 or 16 to 116. And then if I look at my x values, I'm going from 3 to 18. So I can count by ones and make this fit. So I'm just going to label every 4 here. Okay, I'm going to plot them. I won't make you watch me count, but hey, there they are, magic. There are all of your data points. Now you try and make a line that goes as close to them as you possibly can. So sort of like centered, if it won't go through all of them, some above, some below. So that looks, I could do a little better. That looks pretty decent. A couple below, one goes through. It's sort of centered for the middle of my data. Now I'm going to write my equation of that line of best fit by picking 2 points that are on my line. If I try and pick some that have decent coordinates, like that go through a grid intersection point, it'll be easier. So I'm going to say it looks like this line that I drew goes through 1280, and this one's going through 18, it looks like maybe 121. So those aren't points that are in our original set of data points on our scatter plot. That's fine. We're using the points on our line of best fit, and we're going to write the equation of that line of best fit. So we need our slope. So just like in your warm-up, go ahead and do a little rise over run. And it may not come out pretty, and that's okay. My slope's 41/6, so a little bit less than 7. If I find my y-intercept by plugging that in, I can pick either xy pair and plug them in. I'm going to do 1280 for my xy pair to plug in there. Seems a little nicer than 18 and 121. And then I'm going to solve it for my y-intercept. So if I multiply 41/6 times 12, I get 82. And then subtract 82 is going to give me a y-intercept of -2. So there's my equation of my line of best fit. Everybody's equation might be a little bit different, but they should be fairly similar in slope and y-intercept. Now I'm supposed to estimate my y value when x is 20. So let's take that line that I just wrote my equation for and use it to estimate my y value when x is 20. So if I plug 20 into that equation, I'll have 41 over 6 times 20, and then I'm gonna use a calculator for that because I'm lazy. You end up with 134 2/3, which if you kind of look at your line, that makes sense. If we were at 121 for 18, then up at x equals 20 would be about 134.